In our last videos, in our last test, we were testing over the different models of the atom, and we had a problem at the very end with Rutherford's model of the atom, okay? So we're going to start solving that, okay? So I'm going to focus this in here for a minute, and here's what we had. We basically had an atom, and if this is its nucleus, and you had the electron out here like this, there was a problem. The nucleus was basically positive, and the electron, let's say that electron's right there. What should happen over time is positives and negatives attract to each other, and so that electron should spin down until it collapsed into the nucleus and the atom would fall apart, and we know that that doesn't happen. Now, all the things that Rutherford found proved to probably be true, and as he published all those, science knew that it had to be true, but they couldn't solve this problem of why matter doesn't collapse, okay? And so what's going to happen is we're going to work toward a different scientist, and his name is Niels Bohr. Now, interesting thing about Niels Bohr is you know Bohr models, probably from middle school. Bohr models are things that look like this, where you have a nucleus and you have electrons in each of the rings and you would draw it like this. Okay, and that's not a very good atom, I was quickly doing it, but you were drawing and you learn things like this. And if this is an atom, this is a pictorial drawing of an atom, then you have a nucleus, you have 2 electrons in the first ring, 8 in the second, 8 in the third, 8 in the fourth. We'll get into greater detail with that, but Bohr's model, how does that come about? How does that come about? Well, he took what he learned, and we're about to learn right now, from Rutherford's problem, and he solved it. So let's talk about what's going to happen here. First, what we have to do is we have to study the parts of a wave. Now, I'm not talking about a wave goodbye to your grandma, hi, I love you, that kind of wave, doing the wave like in the 80s, not anything like that. We're going to talk about the parts of a wave, okay? And so you're going to need to make sure you label these parts and get this, because it's going to be really important that you get this. Now, the easiest way to do this is, let's pretend we're at the lake. And as you go through the lake, as you go through with a boat, you're going to make waves, okay? Now, before a boat goes by, the lake's flat, okay? This is what we would call resting position. Okay, so the water is just completely flat. And it's easy to talk about water waves because it's something we see. When a wave comes by, you have a top of a wave, which is called the crest. The bottom of a wave is called a trough. If I get ahead of you, just pause the video and catch up to me, and then you can jump back in, okay? Now, how tall a wave is, okay, is called the amplitude. Amplitude. All right, how tall a wave is, okay? Now, if you've ever been on a jet ski or anything like that, when you go in circles, the waves get bigger and bigger and bigger. Or if you've ever been behind a boat and they're pulling you and you're on a raft behind that and they're pulling you along and they want to throw you off, they'll do circles so the waves get bigger and bigger and bigger, okay? And here's why. When you have a crest plus a crest, you get a bigger crest. It gets a lot bigger, okay? Now, what that is called, okay, is constructive interference. Constructive interference. So these waves, if a wave's going this way and a wave's going this way, when they hit each other, they're going to be really big, okay? The same thing is also true. Constructive interference is also when you have a bottom of a wave hit another bottom of a wave, it gets bigger. So think about a hole in the ground. So if you have a hole in the ground and you dig out more, you have a bigger hole in the ground, okay? Now, what actually happens is you can actually have destructive, okay? Oh, I wrote that right, not deconstructive. Let's write this word right. Destructive interference. And that's when you have a crest runs into a trough. So think about it like this. A pile of dirt and a hole. When you throw them together, what do you get? Flat ground, right? Okay, and you're going to see why all of this is important in a minute. Okay, so there's lots of different kinds of waves. So I just talked about dirt waves. We're talking about water waves. Okay, so you have a top of a wave, which is called a crest. The bottom of the wave is called the trough. Now, resting position is actually sometimes called the midpoint. Matt, make sure you get this, because the midpoint means it's the middle. So that means this distance is also an amplitude. Now, I may not have drawn it exactly the same, but if this is the midpoint, then the crest and the trough, how tall this is and how deep it is exactly the same distance, okay? So you can have an amplitude from there. Okay, so you have a crest, trough. Okay, now one wave is considered one crest plus one trough. All right? One full wave is one crest and one trough. So how many waves do I have drawn right here on my board? I have a crest and a trough. That's one wave. Crest and a trough. So I have two waves right here. All right? All right? So I have two waves drawn right here. Now waves, how fast a wave moves, how tall they are, all those kinds of things. Okay, when a hurricane's coming, the more waves come in, the bigger the waves, you have more and more erosion. You're going to have more and more problems with the amount of water that's coming on shore. You have a tsunami, you're going to have a very, very large wave. So that means what's going to literally happen before the tsunami hits is it's going to build a trough. First, it's going to draw all this water off the land, and it's going to get really tall, and it's just going to flood in, okay? So there's lots and lots of kinds of waves. Sound waves work exactly the same way. We're going to talk about that here in a minute, okay? So you're going to have your crest, your trough, your amplitude, okay? You're also going to have what we call the wavelength. Now I'm going to move this word here for a minute so you can see. A wavelength is the distance. So I'm going to write this in there. Wavelength. Wavelength is the distance between two waves. Now you're going to go from the same point. So from crest to crest is a wavelength, or trough to trough is a wavelength, but it's from one place on one wave to the same place on the next wave. So if I started here, then I would be looking there, right? It's a full wave apart, okay? So this is a wavelength, this is a wavelength, this is a wavelength. They're all the same distance, okay? It's the length of a wave, that's all it is, okay? So if there's going to be a hurricane, what do you think happens between the distance and the waves? They're going to come in faster, right? So you're going to smash them together. They're going to come in really fast again. More and more erosion as they hit the ground, okay? As they're coming into shore. That's what does a lot of the damage. Now, the winds do a whole lot, but the water does a lot of damage too. The last term you need to know, and the most important word, is, and notice I put a big bracket around all of it, it's called frequency. Okay? Frequency is the speed of a wave. Okay? So the parts of all waves are a crest, top of the wave, trough, bottom of the wave. The amplitude, how tall the wave is. Okay? It's also how deep it is. The distance between waves is a wavelength, and then frequency. Now, there's all kinds of applications. Some of you guys are like in choir. Okay? And when you sing in choir, what you're trying to do is you're trying to get waves to lay on top of themselves. And what I mean by that is, if you're singing in a section and you're singing a certain note, when the person next to you sings the same note, what's going to happen? Let me show you on the board. I'm going to do a little erasing here for a minute. So when I have this note, and let's say this is the note that I'm singing, and somebody else sings on top of it, okay, and then another person, a whole section of sopranos, the wave's getting bigger and bigger and bigger, which means it's getting louder. But not everybody has to sing really loud. So what are you increasing if the wave's getting bigger? The amplitude. Yeah. And so what happens is when you all sing the same note, it sounds really loud. The same thing's true for band. That's why you tune up before you play. So that when you're playing in the same key, or even playing the same note, when you're playing them, they lay on top of each other. So what's really happening is the waves are laying on top of each other. In reality, what's happening is wave on top of wave on top of wave. It's going to get louder and louder and louder. Not everybody has to play as loud as they can to blast it out if you're in an instrument, but it's going to get louder and louder and louder. But also, so what was this? That's constructive interference, right? That word we had a while ago. They lay on top of each other. Now, if you've ever heard somebody that maybe doesn't sing very well, or they're out of key and the notes are like this, it just doesn't sound good. And you can hear it, the waves. And so you've been trained, some of you have been trained in music, and you hear this woo, 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 woo. It's the sound waves aren't laying on top of each other very well. Okay, and somebody's out of tune, and you can actually hear it. It's because the waves don't lay on top of each other. Okay, so you're starting to have some destructive interference. Now, maybe some of you have been to a concert somewhere and you're going to be sitting, you buy your seat, and it just doesn't sound right. Not all venues, not all places that you go to watch a concert is perfect for a concert. So let's go, say you go to American Airlines Center. Is that made for concerts? No, it's made for athletic events. But they can put a whole lot of people in there. And sometimes when the music's being played, you'll sit in your chair and it just, and you really can't hear. It just doesn't sound right. But the people 2 or 3 chairs down from you are like, yeah, the music's awesome. And you can hear it and it's going great. And how's that happening? Because all the waves bouncing off the walls and off the ceiling are exactly coming to their seat. And it sounds great. But what's happening at yours? You're having destructive interference. So you're sitting in a place where waves are interfering with one another and it just doesn't sound right. Okay? So there's a lot of different applications for waves. Okay? If you have a radio, okay? If you have a radio, you have 2 kinds of radio stations. FM and AM. If I told you the M is modulation, what do you think AM stands for? It's one of those words over there. Amplitude modulation, that's right. So FM is modulation, is frequency modulation. Now, if you know anything about the radio, which one of these waves travel further? AM travels further. Which one has higher quality? FM. So you change the waves, you change the height of the waves, and you send them out, or you change how fast they're moving, because that's frequency. And so you have AM and FM, and you say, well, what about XM? Okay, XM radio or Sirius radio is going to be satellite. So they're not going to send it out from a tower out in all directions. They're going to send it to a satellite and then drop it down to the surface of the earth. Okay, that's why you're going to get TV stations and you have satellite TV, satellite radio, and all that kind of stuff. But they're all coming as waves. As a matter of fact, as you are watching me speak, I want you to just really notice my mouth real quick. Your ears pick up sound very quickly. You see, as I'm speaking, it's actually vibrating air molecules that are going to the microphone. They're being recorded. They're coming out of your speaker, your headphones, into your ear. They go through the 3 bones of your ear to your inner ear. And in your inner ear, there is it looks like a shell, looks like a seashell. It's an organ called the cochlea. And in that cochlea, there are little tiny hairs. And as it goes in there, it vibrates those little hairs and it sends the signal to your brain. And you're hearing me speak. All of that's happening so fast that as you see me speaking, you are hearing the words that are matching it. Sound waves are very, very fast. You can actually have things that go so fast, they're going faster than the speed of sound. And when they go faster than the speed of sound, you have a boom, sonic boom that takes place. So then the sound is actually behind them. Okay? They're actually moving faster than the speed of sound. So there's lots and lots of applications for waves. Okay? Your cell phone runs on waves. Okay, it runs on waves. And so what's happening is you're going to send, the first cell phones went sent out on microwaves. Now, I don't mean your microwaves. Let's do this first. Your microwave in your kitchen, my kitchen's around the corner over here. When you stick something in the microwave, it's sending out such high frequency waves. They're coming in so fast. Those waves are coming in so fast that they actually, okay, for a microwave, they're actually making water, any water that's inside that food, to boil very quickly. As it boils quickly, steam does what to the food? It heats it up. Now, if you've ever used the microwave very much, sometimes you'll put food in there and it just dries it out so much. Here's a hint for you. Wrap it in a paper towel or in a towel that's wet. You wet it at the sink, wrap it up, and then heat it up with a wet paper towel or whatever. So the microwaves, they're heating up the water really fast to make it steam and boil, and it's going to warm up your food, but you don't lose all the moisture, so it's not dried out. Okay? Microwaves is not the box that you put your food in. It's the waves that are being sent out that cook your food. Okay? So your cell phone, as you drive down the road, let's say you're in the road and you're going to go to Dallas. Let's just say going to Dallas. As you pass different towers, your cell phone, even though you're not using it, sends a signal to a tower that says, I'm here, I'm here, I'm here. So that when somebody dials your number is unique to your phone. It goes to the towers and bounces to the towers until it sends the signal to you. Okay? You are literally running on waves. Okay? It's running on, they started out making them with microwaves and they've gotten better at them. Okay? Matter of fact, there are so many, the technology is so awesome that there are so many cell phones and yet we can still use them all. There are allotments, and I'm going to put a quick picture below this video. There are allotments the United States has to allot out from this frequency to this frequency is used for astronomy, from this frequency to this frequency is cell phones. From this frequency to this frequency is used by the military. This frequency to this frequency is used by satellite TV. These frequencies are used for radios. These frequencies are used for television channels. And so they've had to allot them all out so that nobody has the same two frequencies, okay? So you're not driving down the road and make a phone call and it's actually not you. Somebody calls you and they think it's you, but it doesn't come to your phone. So it's allotted to the phone number that you have. And so when you change phone numbers, it's a different frequency. Okay, so it's really interesting. Sound waves, radio waves, microwaves, water waves, they all have these same parts. And what's going to happen is with Rutherford and his idea of the atom, it turned out that waves became important, and here's why. You and I see light waves. Now, all the colors of the rainbow. Now, some of us know this really, really well. Oh, that didn't write correct. Let me do this again. Roy G. Biv. Does anybody know what that is? It's colors of the rainbow in order: red, orange, yellow, green, blue, indigo, and violet. Okay? And so we know that when you run light through a prism, you break it into these. This is where you see a rainbow. After it's rained, you will have this breaking up of light and you see the colors of the rainbow. Okay? So you can use a prism to see the colors of the rainbow. Here's what's really important. Make sure you catch this. Every color of the rainbow is a different frequency. Okay? So, is there just one color red? Girls? No, there's lots and lots of colors of red. And I say that because my wife does hair and nails and does that stuff, has done it for a long time. There are lots of colors of red. How do I know? Have you ever seen the fingernail polish colors? Have you ever seen lipstick colors? There's like fire engine red, candy apple red. And you're like, what's the difference? Blood red. Okay, what are all the apple red? Red apple, what? There's so many colors. They're all slightly different frequencies. So there's lots of frequencies that make red and orange and yellow and green and blue and indigo and violet. You're going to see this in the next video coming up. And what Bohr does, remember his name from a while ago? Is he's going to start connecting the dots. Light waves, sound waves, radio waves, microwaves, water waves, they all have the same parts. But this part ended up being the most important one, frequency, because frequency was related to color. And when you have color and frequency and waves that all have the same parts, he starts figuring out what's happening inside the atom. And in the next video, you're going to see this thing that's called atomic spectra. So I don't want this word to confuse you. Spectra is like the word spectrum. Spectrum, on the spectrum is the rainbow, okay? Atoms giving colors of the rainbow. So make sure you watch that video very closely, how they do that. Atoms give off colors? Yeah, there's some really cool things that we can do, and we'll do some experiments with this where we have atoms giving off colors. So check it out. Waves have frequency. Frequency is related to color. Color is given off by atoms, which means atoms are giving off frequencies. So how do they give off those colors and they give off those frequencies? Bohr was an amazingly smart guy. He was a friend of Einstein's. Okay? He and Einstein and another guy by the name of Planck were all very good friends. Those guys, super smart, started trying to figure out what is an atom, what is a light wave, how do all these things work. So in your next couple of videos, starting here with the parts of a wave, be looking for words like this: frequency, the colors of the rainbow, and atomic spectra. Let's see what you can learn.